Because of buoyancy, the net force on an immersed object is always less than the object's weight. And we remember that the weight of an object is simply its mass in kilograms times the acceleration due to gravity. This net force on an immersed object we're going to call the apparent weight. And the equation for apparent weight is the actual weight of the object due to gravity pulling on it minus the buoyant force that's acting upward, opposite to gravity, so it has a minus sign in front of it. For objects that are floating, the weight is equal to the buoyant force. Well, if the weight and the buoyant force are equal, according to this equation, the apparent weight should be 0. What about objects that aren't floating? Well, for objects that aren't floating, clearly the weight must be greater than the buoyant force. And if the weight is greater than the buoyant force, then the apparent weight must be greater than 0, but less than its actual weight. Let's see if we can show this. Here's an object that's floating. It's got a weight downward due to its mass times gravity, and it's got a buoyant force, which is upward, and in order for this object to be floating, those two numerically have to be equal. This object is completely submerged. You can see that we don't show, well, the surface could be considered to be this one up here. So this object is completely submerged. Perhaps it's resting on the floor of the riverbed or whatever. Its weight is greater than the buoyant force. That's why it doesn't float. Compared to the force required to lift a typical steel anchor to the surface, it takes roughly an additional 17% more oomph to lift it out of the water and into the boat. I don't know if you've ever had this experience. I have. Pulling up the anchor, and it comes up pretty easily, and as it gets closer to the surface, oh, I can see the anchor, it's coming up pretty easily, and as soon as I pull it out of the water, it suddenly seems a heck of a lot heavier. Well, that's because there's no more buoyant force on it helping you lift that anchor up. Let's do a problem. A 43 kilogram rowboat is loaded with 185 kilograms worth of fishers and fishing equipment. What's the buoyant force on the boat when it's out on the lake? Well, we're going to have to assume that the boat, since it's floating, has a buoyant force that's numerically equal to the weight of all of this stuff. The total mass is going to be 43 kilograms plus 185 kilograms of fishers and fishing equipment multiplied by the acceleration due to gravity, 2240 newtons. The buoyant force must be equal to the weight because the boat is floating. What about the buoyant force on a lead sinker like this that we might use if we're fishing? Well, here's the equation. The apparent weight is equal to the actual weight minus the buoyant force. We're looking for the buoyant force. So let's solve that equation for the buoyant force, which means we need to take the weight of this sinker minus the apparent weight. Well, the apparent weight is right here, 0.254 newtons, and the weight due to Earth's gravity is going to be not 28.4, but rather 0.0284, because we have to have the mass in kilograms, times g, and there's our apparent weight coming down right there. The buoyant force on this sinker is 0.025 newtons, and if I were to ask in what direction does that force act, you would say upwards, because the buoyant force always acts upwards. Let's summarize. The relationship between an immersed object's weight, the buoyant force on it, and its apparent weight for both floating and submerged objects is given by the equation apparent weight is equal to actual weight minus the buoyant force.